Previously, we have classified quadratic spaces over p-adic numbers Qp. It turns out that classifications of quadratic spaces over Q can be brought back to the case of classifications of quadratic spaces over Qp because two regular quadratic spaces of the same dimension over Q are isometric if and only if their localization are isometrics at every p. This is an example of the local global principle, which is a consequence of Hasse-Minkowski's theorem. So let us prove Hasse-Minkowski's theorem. Now necessity is obvious. Why is that? That's because V lies inside each of these Vp. So if V is isotropic, i.e. if there is a non-zero vector of V that represents 0, then that same non-zero vector is a non-zero vector of Vp that represents 0, so Vp is also isotropic. In this video, we're going to prove sufficiency for the case of dimension 1 and 2, and we'll prove for the other cases in subsequent videos. But actually, in dimension 1, the statement is vacuously true because V cannot be isotropic. Why is that? Because a vector space of dimension 1 cannot be both isotropic and regular. So let's see why. Well, let's say that we contain a vector, isotropic vector x, so x is non-zero and qx is 0. Because x is non-zero and v is one-dimensional, v is just the span of x. Now, as q of x is 0, that means x is orthogonal to itself and consequently orthogonal to everything in its span. In other words, x is orthogonal to the whole of V, so it's in the radical of V. So the radical of V contains a non-zero vector, and thus V cannot be regular. So for one-dimensional quadratic space, isotropy and regularity are incompatible. Thus, we don't need to consider this case. Now let's look at the case of dimension 2. For convenience, we'll denote this discriminant of V by alpha. Here we want to recall a proposition, the characterization of hyperbolic plane. So for binary quadratic space, we know that the following three things are equivalent. So the space V is isotropic if and only if it's a hyperbolic plane, and that's if and only if the discriminant of V is -1, i.e. it's minus of a square. Thus, it suffices to show that if the discriminant of these Vp are minus of a square mod qp star, right, then it's also a square is minus of a square in q star. So as Vp is isotropic, we know that this discriminant is congruent to -1. So note that this discriminant is still alpha, so we know that alpha is minus of a square of a unit of qp. But what does that mean? That just means that alpha is negative and that the order of vanishing of alpha at any prime p must be even. But if it's true for all prime p, then that means alpha itself must be a square of an element in q, because alpha originally is in q. In other words, this means that the discriminant of V is congruent to -1, so then V itself must be isotropic.